So we've done a few examples using Hess's law, and they weren't too bad. Let's see just how hard these problems can get. I know students complain when the problem on the exam is harder than any of the examples that were ever done in class and on the homework. Well, that won't be the case here. This example is going to be harder than anything you have on the homework or the exam. But it's a great exercise to go through because it's going to illustrate the principles that you will need to do the homework problems and exam problems that you have to do. So let's look at this problem. It asks us to calculate the delta H for the reaction of 1 mole of liquid hydrazine reacting with 1 mole of oxygen gas to make a mole of gaseous nitrogen and 2 moles of liquid water. Given the following data. So these are the reactions where we know the delta H, and we have to somehow add and subtract these reactions to get the target reaction. First one is, if you react 2 moles of gaseous ammonia with 3 moles of dinitrogen monoxide gas, they react to form 4 moles of nitrogen gas and 3 moles of liquid water, and that reaction is exothermic by 1,010 kilojoules. But if you react 1 mole of dinitrogen monoxide gas with 3 moles of hydrogen gas to make a mole of liquid hydrazine and a mole of liquid water, that reaction is exothermic by 317 kilojoules. On the other hand, if you react 2 moles of gaseous ammonia with a half mole of gaseous oxygen to give a mole of liquid hydrazine and a mole of liquid water, that reaction is exothermic by 143 kilojoules. However, if you react a mole of hydrogen and a half mole of oxygen gas to make a mole of liquid water, that reaction is exothermic by 286 kilojoules. So what should I do first? There is one and only one way to start this problem correctly. If you start it any other way, you will probably end up with the wrong answer. So what should I do first? Maybe I should get that 1 mole of liquid hydrazine on the left. How can I do that? Oh, I see liquid hydrazine in the second equation, but it's 1 mole on the right. So I could reverse the second equation and change the sign of its delta H, and that would put a mole of hydrazine on the left. That would work, right? Oh, but there is another way to do it because the hydrazine also appears in the third equation. So I could reverse that one and put a mole of hydrazine on the left. So I guess there's 2 ways to do it. Well, I could take 1/2 of each and reverse them both, and that would put 1 hydrazine on the left. Or I could take -2 of the second equation and +1 of the third equation. That would put 1 mole of hydrazine on the left. Come to think of it, there are an infinite number of ways to combine the second and third equation to get 1 mole of liquid hydrazine on the left. So if I picked one of them, what are the odds that I'd pick the right way of doing it? Not very good. Well, another thing I could try to do is put 2 moles of liquid water on the right. Oh, but water appears in all 4 equations. I'd never guess the right combination of ways to do that. So what's the one thing I can do that can only be done one way? What's the one compound that can only be put in my target equation by doing one thing? Well, the nitrogen gas, it appears only in the first equation. There's only one way to get 1 mole of nitrogen gas on the right. The first equation has 4 moles of nitrogen gas on the right. So if I multiply the first equation by 1/4 and multiply its delta H by 1/4, that has to be right. That's the only way I can get 1 mole of nitrogen gas on the right side. So if I multiply the first equation by 1/4 and multiply its delta H by 1/4, I get -252.5 kilojoules. And I'm going to make a note that I'm doing this because only N2 is unique. So the next thing I want to do is cross out that first equation. I don't want to use it again. I don't want to be tempted to use it again lest I mess up the only thing that I know I have right so far. If I use it again, I'll no longer have exactly 1 mole of nitrogen on the right. So I cross that off, and what's the next thing I can do? Well, I could try getting that 1 mole of hydrazine on the left, but there are 2 source equations that have hydrazine, and I'd never guess the right way to combine them. What about the oxygen? Could I get that? No, there are 2 ways to combine that. How about the water? Oh my gosh, there are 3 ways in addition to the one that I already have in there. No, there's no unique way to get any of the other reagents in that reaction. But there is something I can do next that's unique. There's only one way to do it. In fact, there are 2 things I can do. The source reaction that I used put a ½ mole of ammonia gas and 3/4 of a mole of dinitrogen monoxide gas on the left side of that equation. But I don't want those to show up anywhere in my final equation. I have to find a way to cancel those out. And there's only one way to do that for the ammonia and one way to do that for the dinitrogen monoxide. So both of those are unique. Those are the next things you can do. You can do them in either order. So let's cancel the ammonia first. The only other place that shows up is in the third equation, and it shows up with 2 moles on the left, and we want a ½ a mole on the right. So we're going to multiply that third equation by -1/4, which doesn't mean we put minus coefficients in front of everything. It means we reverse the reaction and multiply it by 1/4. I hope you like fractions. I personally love fractions because we have a lot of them in this problem. So here's what we get when we reverse reaction 3 and multiply it by 1/4. And for the delta H, we'll take -1/4 times the -143 kilojoules of that reaction to get 35.75 kilojoules. And then we can also cancel the dinitrogen monoxide that the first equation put in there, because there's only one way to do that. The only other place that shows up is in equation 2, where we have 1 mole on the left, and what we want is 3/4 of a mole on the right. So we're going to multiply equation 2 by -3/4. Well, multiply it by 3/4 and reverse it, and then we'll multiply the delta H by -3/4. So we're going to cross out the second and third equation. We can't use them anymore lest we mess up what we've already got right. And that leaves only the fourth equation to get everything else right. And if we've done our math right, we can do this in any of 3 different ways. We can use up the hydrogens in a way to cancel the hydrogens that were put in by the third equation, or we can get the oxygens to add up to 1 on the left, or we can get the waters to add up to 2 on the right. So what I'm going to do is cancel out the hydrogen. The fourth equation has 1 hydrogen on the left, and in order to get the hydrogens to cancel, we need 9/4 of a hydrogen on the left. So we're going to multiply equation 4 by 9/4 and multiply its delta H by 9/4. And when we do that, we get -643.5 kilojoules for that equation. So when we add up all the equations, we get our target equation, and when we add up all the delta H's, we get the delta H of our target equation, -622.5 kilojoules. And now let's check and make sure we got everything right. And this is getting a little bit busy here. So let's take out all the stuff we put in to show our work. Now on the exam, you're going to want to show your work. But just for clarity here, let's show the actual equations that we're adding up to give the target equation and make sure everything adds up. So we'll start with the hydrazines. We have 1/4 on the left plus 3/4 on the left, so we got our 1 mole of hydrazine on the left. Let's see if the oxygens add up. We have 9/8 on the left, and we subtract the 1/8 on the right to get 1 mole of oxygen on the left. That works. And what about the nitrogen? Well, we just have that 1 mole on the right, so that works. And what about the two waters? We have waters contributing from all the equations, so we can add up all the fractions. We have 1/4 and 3/4 on the left. We have 3/4 and 9/4 on the right. And one way you can simplify the algebra and reduce the chance of a math error is just like you do in math. You can cancel the 3/4 from both sides. And then when we add them up, we do indeed get 2 moles of water on the right side. All the other compounds have to completely cancel out. We have 9/4 hydrogen on each side, so it's gone. Same for dinitrogen monoxide, 3/4 on each side. And ammonia, 1/2 mole on each side. And where we put the reasons for doing all the steps, when you're showing your work on exams, you don't have to include that. I included it here so you would put it in your notes so you can make sense of this when you go back to study it. So that was a piece of cake, huh?